afternoon session. Please sit down.
Okay.
Okay. So we continue with the third lecture by Herman Verlinde about double-scaled SYK and de Sitter holography.
Just making sure this works. Is it on or not? Is it? Yeah, I should be on. Okay. Okay, so let's continue. So I'll try to sort of, how should I say, stick to the storyline. So because I have quite a few things to talk about, I'll try to explain what I think is sort of the most convincing argument that starts linking the SYK model. First of all, I'll explain how to compute the correlation functions, what the structure is that allows one to do this, and then I'm going to try to directly relate to the structure that comes out of SYK by starting on the de Sitter gravity side. So I'll try to have a rather direct link between the two. So there's a beautiful paper by Berkus, and three co-authors, and Flansky, and I'm sorry if I forgot the other two, where they actually solve the SYK model in a combinatorial approach. As I was mentioning before, in the case of this equivalence with the Liouville theory, it turns out that you can solve the Liouville theory by just expanding the interaction Hamiltonian, or the interaction term. You can also directly start from the SYK model, just treat it as a bunch of free oscillators. And the object that you want to start computing is what you would call the moments of the Hamiltonian, where you just take the trace over the Hilbert space of this a bunch of fermions of a product of a bunch of Hamiltonians. Later on, we're also going to introduce other operators that we want to insert here, but let's start with this one, because this should be enough to compute the thermal partition function. And then, as I sort of try to argue, this circle is the circle that's represented by the trace. I can think about it, say, as a path integral, where the trace becomes that circle. And then any of those h's, they live on that circle in the order that they're placed over here. And then, because the j's are Gaussian random variables, I'm starting to do Wick contractions. Again, there's a sum over the indices here. But those Wick contractions, essentially because of large n, have to sort of start connecting each individual term that looks like this as a whole needs to be Wick contracted with another term exactly like that appears in another Hamiltonian. So this is called a chord. But then, of course, you're going to have different Wick contractions, and those Wick contractions can lead to intersections. And that's really where things are happening, because if they don't intersect, then the Wick contraction is basically just one, and at least normalized appropriately in units where this j squared, say, averages to 1. So let's forget about the powers of j squared for a moment, because the fermion propagators just are a sign function, and it's precisely the sign function that's important, because at the intersection, there's a certain probability that there's an overlapping set of fermions in that Wick contraction. And when that happens, there could be a minus sign that can start showing up because of Fermi statistics. Now, again, in the double scaling limit, where p squared over n, which is called lambda, is kept fixed, a little bit of combinatorics, and I'm going to write down the formula for you, shows that the contribution of two of these intersecting lines is slightly suppressed relative to the contribution where they don't intersect because of minus signs that start showing up. The probability of a minus sign showing up is actually p squared over n to some extent, because there are p fermions here, there are p fermions there, and at the intersection there are p squared fermions that could potentially have an overlapping index. And since there are in total n of these oscillators, the probability of two lines intersecting that have the same index is basically p squared over n. But there could be multiple fermions that have overlapping index, and that becomes a Poisson distribution. So the overlap will be suppressed by a number that I'm going to call Q, and that number is as follows. It's Poisson distributed, indeed, with probability p squared over n. But then I could have multiple overlapping indices. Say if there could be k overlapping indices over this. And this I have to sum over k. And importantly, there's going to be a minus sign for every intersection. And if I do this sum, I get e to the minus 2p squared over n. So that's the basic observation, is that if you start doing the Wick contractions and you produce these things that are called chords, those chords again are sort of a multiple Wick contraction. Then when those chords intersect, you pick up a factor of q. Now q is a real number less than 1. And the only thing that we now need to do is to just sum over all possible chords again, and then counting intersections with this factor of q. Okay? Are there questions about this logic? Because now I'm going to do the counting. Okay? So the counting is done, again, in a very clever way. Basically, what you're doing is you're going to introduce an auxiliary Hilbert space by cutting the, this thermal circle into two halves. It's a bit like a thermal field double type state, but anyway, I'm going to cut it into two halves, and I'm going to just create a Hilbert space on this intersection here. But the basis of the Hilbert space is just, you can call it the chord number basis. So the auxiliary Hilbert space that I'm going to introduce will just have n as a set of basis elements, where n counts the number of chords that intersect this line. And then what we want to know is how does the Hamiltonian act on this chord basis. And now what we're going to do is we're going to basically think about this horizontal direction sort of as a little bit as a time direction. So let me straighten out that half circle like this. And here again I have a bunch of Hamiltonians that are acting, H, H, H. But suppose I consider some segment in this half circle where there were already a bunch of chords. So the horizontal line here are chords that were already present at a certain time. And as you can see, the Hamiltonian can do actually one of two things. It can either be the endpoint of a chord, or it can create a chord. Okay? And then, sort of to have a unique ordering in the whole story, we're going to have a convention that if a Hamiltonian creates a chord, that it will do it on the lowest rung. So what that means is that if H acts on this state n, then one thing it can do is it can raise the chord number by 1. Okay, like that. But then at some point there's going to be one of the Hamiltonians that decides to annihilate, or this one may also annihilate, one of these chords. So when the Hamiltonian annihilates a chord, there are different possibilities of where the chord is coming from. So it will indeed annihilate a chord, so there's a term that's proportional to n minus 1. But what's in front of this thing is basically going to be a geometric series where for every intersection I need to have a power of q. But indeed, if I have n chords to begin with, this geometric series is between 0 and n. So I sum q to the k from 0 to n, which is equal to, or to n minus 1 perhaps, or n plus 1 maybe, divided by q. Is it n? Thank you. Yeah, right, I got confused. So the sum goes to n minus 1. This thing here is called a q integer. So we're going to think of q actually as a deformation parameter. And indeed, in the strict large n limit, q is going to be equal to 1. But if we think about q as a quantum deformation of the theory, and that's sort of suggested, indeed, by this thing is called actually a quantum integer. So I can call this thing nq. That's the definition of that thing. And the q to 1 limit of n sub q is just n. Okay. Now, it turns out that this is the whole story. Basically, this is a Hamiltonian that acts on this basis n, and my task is to compute the spectrum of this Hamiltonian. Okay. Now, are there questions about this equation? Because this is, again, the whole story almost, and everything follows from this. Yes?
Can you go over why the NQ is a geometric series again?
Basically, because if I have one of these Hamiltonians, it can absorb a chord. It can annihilate it. But in the normalization, in the convention that I'm choosing, when they are created, they're on the lowest rung. But when they're annihilated, they can come from anywhere. And anywhere means from 1 to n minus 1. And that leads to, or actually from 0 to n minus 1 maybe, the number of chord intersections. And if I sum q to the k from 1 to n minus 1, this is why I get this.
I have a question about the general organization principle of the correlation functions here. Because in the general Topf limit, we have typically a topological organization principle such as planar diagrams, or in the usual SYK model, it's the Milonic diagrams. So what's the analogous principle here in the double scale limit?
Yeah, okay, it's a good question. Let me just give maybe the answer by considering two limits, okay? One limit that I can do is I can take q equals 0. If I take q equals 0, I'm actually going to forbid intersections. And then actually all my chord diagrams will become planar diagrams because I cannot have intersections anymore. So it's a bit like a large n limit, and since these are just sort of Wick contractions, indeed it turns out that the equations that I'm writing down here, the spectral density that I'm going to find in the q to 0 limit will become actually the weakness semicircle of a Gaussian random matrix. So q to 0 is the Gaussian matrix model. Q to 1 means that I'm just doing free fields. There's nothing, at least no suppression anymore. Then it's just a free theory. So this is sort of interpolating between just a non-planar free theory to a thing that's completely planar. The combinatorial rules actually show up in something that's called free probability theory. The free limit is the q to 0 limit. But this is sort of a more generalized type of probability. And it was studied by various people, and there's a paper by Erdős and Schroeder, unrelated to SYK, that already solved the combinatorics of this. And there are even papers in the 90s where people basically already had this particular combinatorics. It just happens that in the double scaling limit, you get this particular combinatorics. And the key thing here, again, for those of you who already sort of draw the conclusion that when this thing is just an actual integer, this looks like a harmonic oscillator. Indeed, I have sort of the oscillator levels. And this is then the raising operator, and this is the lowering operator if I slightly renormalize my states. Okay? And this is exactly the idea of how we're going to be solving this theory, because it turns out that basically what I can do is I can define a raising operator and a lowering operator. Let me call it still AQ and AQ, such that the, let me do this right. You know what, I'm not going to write down the Q here. It's a Q-deformed algebra that if this relation is true, I call this a Q-deformed oscillator. And essentially what this equation tells me is that after indeed taking into account this factor of 1 minus q and doing this thing properly in terms of normalization, then this thing is an A dagger, that thing is an A, and I think the only thing I need to do is divide by a square root of 1 minus q. So it turns out that if I introduce this algebra, and I make a representation of this algebra in the usual way, where in this case, I'm normalizing my states so that A on this thing is n q n minus 1, and maybe with a factor of square root of 1 minus q in front of it, and square root of 1 minus q A dagger on n is n plus 1. And you can verify that these two operators satisfy this particular commutation relations. So this is a Q-deformed simple harmonic oscillator. And basically what we have to do is we have to solve for the spectrum of a Q-deformed harmonic oscillator. However, as I said, H looks like this. So I'm not going to be solving for the spectrum of the usual simple harmonic oscillator Hamiltonian, which would be A dagger A. I'm going to be solving for the spectrum for the operator that's the analog of X, of the position operator of harmonic oscillator. Okay. Not surprisingly, again, if I think of Q as a number that's extremely close to 1, the spectrum that I'm going to find for this particular operator is essentially going to be the Gaussian, which is the ground state of the harmonic oscillator. So let me go and do that. Unless again there are questions on this point. So part of the trick is to do exactly what you learned in your undergraduate quantum mechanics. You start thinking about Hermite polynomials, and there's a Q-deformed version of it, and the Q-deformed version of a Hermite polynomial. So the Hermite polynomial, maybe we'll call them little h sub n. They depend on a variable, say x, and they also depend on q. And the relation that they satisfy is that if I add 1 and indeed they satisfy a recursion relation like so. And indeed, again, if you take the q to 1 limit, this turns out to be the ordinary Hermite polynomials. And basically, the idea is that if I'm going to be looking for an eigenstate of the Hamiltonian, I'm going to call the eigenstate. So there's one. I should mention one thing. Although this is the definition of the Q-Hermite polynomials, it turns out to be natural to restrict, that the value of x actually is going to be restricted between 0 and, okay, let me write it down. There's going to be energy eigenstates, I claim, that whose eigenvalue can be parameterized as follows. By the way, there's another coefficient thing here. The lambda should go here too. Sorry, I forgot that here. I claim that the spectrum of the theory is going to be given by this. So the energy eigenvalues. So this quantity 2 cosine is theta cosine divided by this thing is the analog that for the harmonic oscillator would be just the position operator. Just as for the harmonic oscillator, this position operator is indeed a continuous variable. So the energy spectrum is going to be continuous. Except that the new thing, because of the Q deformation, is going to be is that there's an upper limit on the eigenvalue of the Hamiltonian. Whereas for the harmonic oscillator, the position operator could go from minus infinity to infinity. Now, the question, or at least the thing that we want to determine, is what is the spectral density on this. For the Q Hermite polynomials, or for the Hermite polynomials, they satisfy an orthogonality condition. If I normalize the Hermite polynomials, the orthogonality condition, there's going to be some integration measure, which for the ordinary Hamiltonian would be the Gaussian, which is the ground state of the Hamiltonian, times hn of x, let me suppress the Q notation, times hm of x. It turns out that with this normalization, this thing is going to be, I think, nq factorial. Where nq factorial satisfies the usual condition, recursive relation of a factorial, but now again with the q integers defined. And then it turns out that this spectral density, rho of x, if I write it in terms of that theta, turns out to be given by the following. Given by a thing that's called the hammer symbol. Where ZQ is the product of n equals 0 to infinity, 1 minus ZQ2. So it's a slightly indirect way of starting to think about the spectrum. So let me call this thing rho of theta. Maybe that's a better way notation for now. So that rho of theta, it appears indeed in the orthogonality condition of the Hermite polynomials, but the claim is that this is actually going to be the spectrum of this particular theory, because indeed it's the natural spectral density associated with this Q-deformed harmonic oscillator. Now this expression looks slightly unfamiliar. For those of you who know about Riemann theta functions, it turns out indeed that if I write this thing in terms of the energy, so let me call this thing indeed the energy, then up to an overall prefactor, this thing actually is equal to, and I apologize, there's going to be a theta function, which is the curly theta, of e to the I theta 2 theta Q. And that theta function actually is known to have this particular form up to a prefactor of sine theta that comes from the fact that here I'm writing it as a function of theta. Here I'm writing it as a function of this variable cosine theta. Sorry?
I'm wondering, in this density formula, shouldn't this theta also be divided by a Dedekind eta function, because the usual theta has also a piece which is like 1 minus q to the n.
Right. Let me sort of take the fifth on that question a little bit, because it turns out that if I do this whole thing, and the logic by which I sort of derive at the spectral density, it kind of bypasses a particular point. In the end, I'm interested in the spectral density of the actual SYK model. And here I'm introducing what I call this auxiliary Hilbert space, which is this chord basis Hilbert space. Obviously, this Hilbert space that's labeled by these integers is much smaller than the Hilbert space of the actual SYK model. If you wish, this commutator algebra of the Q-deformed harmonic oscillator is only a very small sub-algebra of the full operator algebra of this particular theory. I can write down many, many operators in this theory that don't look like that. In addition, I'm taking this double scaling limit where n goes to infinity and p goes to infinity, keeping this ratio finite. And in that limit, you should not expect to be able to find the full exact level density. Basically, the level density should be proportional to the dimension of the Hilbert space, which we knew was 2 to the n over 2. So the entropy, the ground state entropy, if you wish, of this theory should be proportional to n. Whereas this turns out that this particular expression is bounded by 1 over lambda. So it's in terms of the entropy is going to be much smaller than n. So in general, what's going to happen is that there's going to be a pre-coefficient in this spectral density that I haven't determined through my logic. So anything that would be a constant that does not depend on theta, I'm just going to absorb in that particular pre-coefficient. For the experts, it turns out that indeed if you do this double scaling limit, mathematicians again have studied this whole thing. And it turns out that this particular algebra here is a type 2 von Neumann algebra. And for the experts, for those type of algebras, you cannot determine the entropy. You can only determine it up to an overall shift. And that's what this S0 is. Now, the interesting property of this theta function, it's actually essentially a periodic Gaussian factor. So it looks like a Gaussian, indeed, what you would have expected on the basis of the fact that it's a harmonic oscillator. Let's think about the energy spectrum first. The energy spectrum, so if horizontal is again theta, and vertical is E of theta, we know what a cosine looks like. Actually, sorry, there should have been a minus sign here. Forgot about that. So indeed, at theta equals 0, the energy is minus this 1 over this quantity here. When theta equals pi, it has a maximum. So it's natural to restrict theta again between 0 and pi. And when theta is pi over 2, that's when this cosine is equal to 0. So that's what the energy spectrum looks like. And on this same scale between 0 and pi, this function here looks as follows. It starts at 0. It goes up. It basically behaves like a Gaussian. And it again goes to 0. So this is theta equals pi. Theta equals pi over 2. And this height here is roughly of the order 2 over lambda. to the power 2 over lambda times the S naught. But at least what I'm saying is that this theta function, it becomes like e to the power 2 over lambda at this value. Okay, so that's what the spectrum looks like. And this is sort of the exact spectrum of the double-scaled SYK model. And I'm going to be interested, my question that I'm sort of interested in, what is the geometric explanation? What is the underlying geometry that explains this? Because I started with a quantum system that's over there. I took the double scaling limit. I get this effective description, that's the large N limit, and it produces this particular spectrum, and this should be geometric. Okay. Now, we see a bunch of features. We need to see a point of maximal entropy. We see actually that this point is going to be a point where the energy indeed is still changing as a function of theta, but the entropy does not change as a function of theta. So it means that if I would compute the temperature, the inverse temperature beta, which is the S, so what I put here vertically, again, is e to the power what I call S of E. If I differentiate S with respect to E, I get the inverse temperature. But that thing is equal to 0 up here, so this is an infinite temperature point. Strikingly, again, here in this region, again, the temperature is negative. Here the temperature is positive. Another slightly striking feature, although my drawing didn't quite reflect that, is that this thing is actually symmetric between E and minus E. Now, to me, this is already an indication that in terms of the holographic dual, indeed, I should not be looking for ADS space. I should be looking for another space that has a natural maximal entropy state. And it turns out that indeed many people that know about the SYK model are aware of the fact that this is actually a model, and this is why we got excited about the SYK model, that it's actually also a good holographic dual for what we call near ADS2 holography. I'm interested indeed in this model by studying the full range of the spectrum between 0 and pi. So I really want to study the whole model. And in particular, I want to study it in the region where the temperature is high. A lot of the early literature on the field was actually taking the large N limit. So they took the Q to 1 limit of the theory. But in addition, they took the temperature to be small, so that in the Q to 1 limit, one typically only was looking at this little corner of the spectrum. And it turns out that in that little corner of the spectrum, that this spectral density is actually proportional to the sine of the square root of the energy. And the formulas that I have here actually behave that way. And that's exactly the spectrum that you have in ADS in an anti-de Sitter space. So this little corner looks a little bit like anti-de Sitter space. But all of this here does not look like anti-de Sitter space, because in anti-de Sitter space, this line would keep growing forever. Okay. So that's, again, a first indication of at least new physics. Maybe I'm going to leave this for now when it comes to the SYK model. You can do more general things where you can introduce other types of quartz. The quick logic is that you can introduce matter fields that essentially look like this, except that P doesn't need to be P. It can be some other number. What I call matter fields are just local operators that look like O, again, some sum over coefficients, random coefficients up to, say, an OP prime of a bunch of Majorana oscillators. And this thing, again, will behave like a field. We call it actually O delta, where delta is P prime over P. And delta indeed behaves sort of like the conformal dimension, a scaling dimension of that operator. And what you could do is you could insert O in this correlation function. And again, you're going to find the same type of chord rules, except that the intersection will no longer be labeled by this Q, but they're going to be labeled by some q tilde, which is basically this q to the power delta. So you can have also matter chords. And then a little bit more calculation allows you to exactly compute the correlation functions as well. But what I would like to do is I would like to basically now jump indeed to de Sitter gravity and derive for you this algebra from de Sitter gravity. And basically it will tell you that I can at least reconstruct the spectrum from de Sitter gravity. The matter operator, as I mentioned, this thing here, is sort of represented in the same algebra. Maybe I should still mention that, is in the following way, that a two-point function of a matter operator with O, O, so O, O, and if O delta sits here, say, or let me put it on this side here. So if O delta sits here, and the other O delta sits here, then the other operator that might still be interesting to study is actually an operator that creates a chord that goes between here and there, where all the intersections that are taking place here are labeled, suppressed by a factor of q tilde, which is q to the power delta. So essentially this operator actually is q to the power n times delta, where n counts the number of chords. So this is the way in which matter can be included in the description. Yes?
A dagger, simply the dagger of A?
Not quite in this basis,
Okay.
but there is a basis where A dagger is the dagger of A.
I was just trying to check that the creation annihilation relations that you've written down are consistent with the algebra that you wrote down. In order to do that, I wasn't able. I didn't see why those are consistent.
I have this n factorial here. So the only unusual thing relative to the usual harmonic oscillator is that this n basis is not normalized to 1. Nm is not delta nm, but it's delta nm times, actually, I should have written that down here, delta nm times this n factorial. So this n factorial leads to this slight asymmetry, but this is sort of a more natural place to jump in from the point of view of the. So for the Q-defined harmonic oscillators, you might have labeled these states slightly different.
Sorry, very quickly. Are you restricted theta in 0 to pi to avoid degeneracy, or is it just the way it is?
Also a very good question. The question is, indeed, could it be that there are actually many energy eigenstates just by having this theta just keep going up and down? It so happens that the spectral density rather naturally is a periodic function of theta. It turns out that if you compute correlation functions, also those correlation functions end up being periodic functions, at least integrals over theta of periodic functions of theta. But it might be possible to think about it differently, but it turns out that everything essentially can in the end be packaged in a form that is compatible with the fact that theta only lives over a finite range.
So at this point, you declare it to live in a finite range?
No, another, let me give you a stronger argument. It turns out that this particular spectral density actually turns negative as soon as I go beyond this point. So I'm just focusing on the part of the region where the spectral density is positive and makes sense. Okay, so how am I doing with time?
Just another quick question. Yeah. I mean, without going through all this, is there some intuition to see why a Jacobi theta shows up?
As I mentioned, there's a formula which I couldn't write down for you for a theta function. And that formula algebraically, it's because the theta function satisfies certain quasi-periodicity conditions that are compatible precisely with the relationship that sort of this thing needs to satisfy. But from a physics perspective, the following formula I find actually quite useful. That theta function that I'm writing down there, e to the 2I theta q I'm hoping I'm getting this one right. Maybe up to some prefactors. It's a sum over all integers minus 1 to the n e to the 2 over lambda theta minus n plus a half pi, right? Something like that. So it's a periodic a Gaussian.
Yeah, so I think you answered my question.
So indeed, if theta if theta is in that particular range between 0 and pi, then the n equals 0 thing of this thing dominates. But there are kind of higher saddle points that are displaced by pi.
Yeah, I think you answered my question in the first half itself, because I was trying to wonder, I was wondering because theta functions usually show up when you have a lattice problem, when there is a periodicity. I guess you answered that by just saying that this recursion relation gives you some sort of periodicity, and the only solution is a...
Right. But this periodicity is very good that you guys are focusing on this, because in the end the claim is going to be is that there has to be some dual system, gravity system, for which this one is a spectrum. So if I'm serious about it, then indeed I should already from the start, by looking at my gravity system, understand why the spectrum is finite and why there's a variable theta that's naturally sort of bounded between 0 and pi, or 0, yeah. And the basic proposal is going to be that indeed the Schwarzschild-de Sitter metric that I was talking about 2 lectures ago. So the Schwarzschild-de Sitter spacetime is indeed labeled by an angle theta, which is what I call the deficit angle. So that's going to be my sort of starting point. But then there's a second starting point, namely that there is this variable q, which is a real number between 0 and 1. I also had the story from the lecture this morning that there is a Liouville theory in all of this, where indeed the central charge of that Liouville theory, at least suggestively, might look as follows in terms of this, again, bad notation with the beta. Let me still keep that one. But maybe more importantly, there was this parameter b that was e to the I pi over 4 because of the Liouville theory having this wrong factor of I in front of it. So b squared is imaginary, and normally in Liouville theory, it turns out that many of the Liouville correlation functions also have a q factor in it. Let me call this thing q Liouville. And that q factor is typically written as e to the I pi times b squared. But if b squared is imaginary, then indeed this thing becomes e to the minus pi b squared, and indeed it's a number less than 1. But indeed, it forces me to think about this Liouville theory with a complex central charge. But now let's go to 2 plus 1 gravity. And so, again, I was drawing the Sitter space for you yesterday, and one way of thinking about it, again, is just as this hyperbolic space. But I'm going to do this now in 3 dimensions. If I slice it through the middle here, this spatial section is a 2-sphere. So let me draw that 2-sphere for you. So this is space. This is the set of space-time. So this is a spatial slice. Now, I already explained that you can have this static patch. So if I take the origin of the static patch, and maybe I should use a yellow color here, to be this particular line, then that line intersects that sphere here at the North Pole. for every point, for every observer in the zeta space that's static, there's an antipodal observer that sits on the opposite side. Often one thinks about time going backwards on the opposite side, so here time goes up, here time goes down. Because indeed, at the halfway point, that's where the observer horizon for this thing sits, for this observer sits. And the static patch is basically this little triangle of the de Sitter space-time. But that triangle intersects, indeed, this sphere at the equator. So the static patch is basically, say, the north patch of this sphere, whereas this left region here is the south pole patch. So indeed, I'm going to call this thing the north pole and this thing the south pole. And basically what I would like to do is I would like to do quantum gravity on this space-time, where basically I have to take the Einstein action and ask, well, what is the phase space of this theory? And how do I quantize that phase space? So I want to quantize 2 + 1 gravity on this space-time. But the additional ingredient that I'm going to give myself is that I'm going to have, say, think about it as an observer that sits, one that sits at the North Pole and one that sits on the South Pole. And the reason I'm going to do that is because I want to be able to introduce observables. Now, we already talked about the Schwarzschild de Sitter spacetime. The Schwarzschild de Sitter spacetime, and it has a conical deficit that sits at the North Pole and the South Pole. So there's one observable that I can very naturally introduce. And that observable is basically what I would call the gravitational Wilson line that goes around the equator. What I mean by the gravitational Wilson line is that if I am a local observer and I sit at the equator, then locally the space-time will look like the Sitter space-time, because essentially in the Sitter gravity, why not actually write down the action, although I always get nervous about signs in this whole business. But I think what I'm going to do, right, so that's the Einstein action in 3 dimensions. And in some units, at least, the equation of motion might be that the curvature is equal to 2 or 1, but I think it might be, or is it 1? But anyway, it's a constant curvature metric. And locally, that, again, looks like the Sitter space. But then if I go around, my coordinate system will have detected that there's an angle deficit there. And therefore, that Wilson line will basically observe a rotation. And so I'm going to introduce an observable that I call W, which is basically the trace of the rotation matrix that I have to perform if I go around the equator. So there's some rotation matrix, cosine theta, sine theta, cosine theta, minus sine theta. Over here, it's a 2 by 2 matrix. I take that trace, and I get something like 2 cosine theta. Okay? So this theta is a variable of my phase space of this gravity theory, because it's something that I can measure. Okay? Are there questions about this?
Is this Wilson line topological in the sense that wherever you compute it, you get the same, or you have to compute it at the equator?
I prefer to think about it as the equator, but it's topological. Indeed, anywhere I sit here, I get the same answer, because indeed it's just a transition function between two coordinate patches. And indeed, clearly, if I'm sort of close to the equator, I still see to the North Pole, I still see the same deficit angle. So it's indeed literally topological. So it's a good question. Okay, so let me do another thing. I want to know the phase space of the 2D gravity of the 2 + 1D gravity theory, and it turns out to be convenient, but not essential. to think about this Einstein action from the point of view that Witten kind of introduced in the late 80s, where I can write this thing in what you might want to call a first-order formalism, where instead of using a metric, I'm going to be introducing a dry bind, or whatever you want to call it, a tetrad. So there will be a three-component frame field, and there will be a spin connection. Dxi. Let me call this thing omega, call this thing E. And then it turns out that the Einstein action in 2 + 1, the zeta gravity, is naturally written in terms of what in the end turns out to be essentially a complex gauge field, which naturally is essentially obtained by taking these linear combinations between omega plus IE and omega minus IE. And then what this thing looks like, it looks as follows. It's let me call it kappa, and there might be a 2 pi here. Integral trace A dA plus 2/3 A cubed minus the same thing, the bar. If you work out this particular action, you plug in this parameterization, you're going to get some action in terms of the E and the omega. If you solve for omega through its equation of motion and eliminate omega through its equation of motion, you plug it back into the action, you get an action that only depends on actually the local Lorentz symmetric combination of E, which actually is the metric. And then so after eliminating omega, you get back to this particular action. Okay? Many people immediately start complaining that, oh, that doesn't mean that this theory is equivalent to that theory. Because, for example, I'm going to be treating this a little bit as a gauge theory. If you would treat it as a gauge theory, then there's no reason for why E has to be invertible. Whereas in gravity, we do want E to be invertible, an invertible metric, or at least the metric to be invertible. But what I'm going to do is I'm going to do essentially what I was doing here already on the picture that I was drawing here. In the end, this theory, indeed, if I treat it as a gauge theory, it's topological. And the observables, let me first say the following. The equation of motion of this theory will be that this gauge field is flat. I'm going to finish my story. I also have gauge symmetry. Normally in gravity we have diffeomorphism invariance. In this case, the gauge symmetry of this theory is SL2C. Just again for the experts, or at least for as an aside remark, you can do the exact same thing for anti-de Sitter gravity. You can also write it in this form. In that case, the gauge group of the theory is SL2R times SL2R. In this case, it's SL2C. And indeed, this thing is the complex conjugate of that thing. If I divide out by gauge invariance, the gauge symmetry, then you can show that this theory is actually topological. There are no local degrees of freedom. And that's also true for the gravity. There's no local graviton. You have a unique solution to the equation of motion. The same is true here. The only thing that can happen is that if you have non-trivial topology, and if you have non-trivial topology, then your observables are going to be operators that are line operators, which have to be gauge invariant. So they have to be path-ordered exponentials of the gauge field around some appropriately chosen set of loops that reflect the topology of my spacetime. Are there questions about this statement? Okay. Yes. Yeah, so this thing, indeed, is that your question? Yeah, so indeed, so the idea is the following, is that when I'm talking about the phase space, what I have to do is I have to construct the phase space of this theory. And the phase space has to be something that knows about, again, what space-time I'm on. And then, indeed, for every cycle, I should have a line operator that I want to be able to introduce. The key thing that needs to happen, of course, is that if I have one coordinate on a phase space, I should find at least another coordinate that it's momentum associated with one. So a phase space is even dimensional. So the thing that motivated me actually when I started thinking about this to introduce the North and the South Pole is that at least I want to be able to find a dual Wilson line operator, and it's going to be a line operator that goes between the North and the South Pole. But you're right that this thing here is going to be the trace around the equator. Let me call that thing the A cycle, the trace of the path-ordered exponential of that Wilson line around A, like so. But if you wish, I can also still stick to this definition, where it's just defined in terms of the transition function of my space-time. So the fact that I'm writing it as a Wilson line, you'll see in a little bit later why that's useful. And the only thing that I'm using the Chern-Simons formulation for is actually for two things. One is to actually get a little bit of a hint of how this thing is going to be related to this Liouville theory that I wrote down earlier. And the other thing is that it's going to allow me to compute Poisson brackets, or to actually quantize the phase space in a way that's very immediate. Because Chern-Simons theories are actually well sort of studied when it comes to how to compute commutators and things like that. Are there other questions?
Omega the Hodge dual of the spin connection?
Sorry?
Is omega the Hodge dual of the spin connection?
Of the spin connection? Yeah, right. It is. Because normally it has two components, and then in 3 dimensions I can take the epsilon symbol and give it one component. That's right. At least in the internal indices. Yep. Other questions? This one here.
Yeah, I'm sorry. I'm a bit confused. I mean, so you said that the topology of your space slice is like, of your time slice is like a sphere, right?
Yeah.
So I don't there should be like no non-trivial loops. So the holonomy isn't trivial.
Sorry, there should be?
I am expecting to have like no non-contractible loops.
Yeah, but that's, I'm putting deliberately my north and south pole here.
I'm sorry, can you repeat?
So I'm putting a north and a south pole here, and I'm making this thing sort of a place where I no longer allow for gauge transformations, and I'm allowed to give to put a curvature singularity here.
Okay, so
then this loop becomes non-contractible, and that's why it can have a non-zero holonomy.
Thank you.
Okay, let me see. I'll try to fit what I want to do in 15 minutes, which means that I'm going to make the following remark very quickly. It turns out that in Chern-Simons theory, you also naturally have a Q factor. So normally, if you write down Chern-Simons theory, you do SU2 Chern-Simons theory, or you might even do SL2R Chern-Simons theory. And then it turns out that the properties of the Wilson lines in Chern-Simons theory, they can be used to make knot polynomials. And the knot polynomials also are expressed into polynomials in a variable called Q. And if the level of the Chern-Simons theory is real, then in Chern-Simons theory, so let me call that Q of Chern-Simons, normally for a thing with a real level, it's 2 pi I over k, or maybe shifted by 2k plus 2 or something like that. But the Q factor of Chern-Simons is typically a phase, and this leads to quantum groups with a Q deformation that's a phase. However, in the case of the Chern-Simons theory that relates to de Sitter gravity, this thing is known to be a complex level. So this is SO2C Chern-Simons theory at complex level, at imaginary level. Okay. So in this particular theory, the Q factor is e to the 2 minus 2 pi over kappa. So at least I can already see that precisely the same relationship might hold. And indeed, people have done calculations where they computed, say, the partition function of this theory on a cylinder. And then in the same way as that you can compute the partition function of ADS3 gravity on a cylinder, where you're matching it with the partition function of a CFT with real central charge, what you're going to find if you compute the partition function of this theory on a cylinder, you're going to find that the boundary theory indeed is a CFT. You exactly find the shift by 13. That's a one-loop effect. Turns out people have done that calculation. So this theory naturally lives on the boundary. It's the edge mode theory of this particular theory. One thing that will become a bit important, and I'll probably have to discuss that in the next lecture on Thursday, that if I want to start doing the analog of ADS CFT, but now with gravity on the Sitter space, one difference between the Sitter gravity, which is really natural for the Sitter space, is that, as I mentioned, the boundary, what I call the edge modes, naturally live in the future and in the past. So my complex Liouville theory, to some extent, lives on the future and the past. But unlike in ADS CFT, where I can actually fix the boundary condition, in DS CFT, the bulk path integral, or let's say it this way, the CFT that lives over here does not give me the partition function of this theory. It actually gives me a wave function of the theory. And the physical quantities that one can compute in the Sitter gravity are not the wave function. The wave function is not a physical quantity. I have to be able to take expectation values, which means that I have to be able to take an inner product between two wave functions. And what's very nice about this particular theory is that the edge modes, indeed, will give me two Liouville theories, because one Liouville theory comes from this term, the other one comes from that term, and indeed they will have complex conjugate central charge that adds up to 26. And that's a magic number, because it's also the critical dimension in string theory. And it means that the thing that we're going to be doing, and I'll discuss that again on Thursday, is that from the point of view of the boundary theory, I have to treat this thing as a gravity theory, where indeed I take C plus C minus equals 26, and later I'm going to be adding a BC ghost system and integrate over the boundary metrics. So that's a comment. But in the last 10 minutes, what I would like to do is I would like to be able to reproduce for you the Q-deformed harmonic oscillator based on quantizing this space. Okay? So maybe rather than telling you exactly what I'm going to do over here, let me give you one little piece of information, which is generally true for this theory. Whenever you have a gauge theory whose gauge group is rank 2, so it's SL2R, SL2C, or SU2, it's possible, indeed, to define Wilson lines in the spin 1/2 representation of the SL2. So let me define these loop operators. And the thing that I would like to be able to do is to compute the commutator between these things. Okay. Now that has been done, certainly for SU2, because this is exactly the technology that people developed to compute the Jones polynomial. In this case, what I'm interested in is actually going to be the commutation relation between these guys. And in general, in gauge theory, indeed, if I have Wilson lines, typically what we do to compute the commutator between Wilson lines is we project it first on a plane. We look at the 3D Wilson line, and suppose that I have two Wilson lines that cross each other, where one Wilson line goes below the other one, or it could go above the other one. So indeed, this is a crossing of two Wilson lines. And then it turns out that there's a natural relationship. If this were not a quantum theory, but a classical theory, it turns out that if I have an intersection between these two Wilson lines, then just by the group theory properties of a 2x2 matrix, you can actually show that this thing is equivalent to doing this. So these are two spin 1/2 Wilson lines. They cross, and I can uncross them. This is just the fact of 2x2 matrices that I can do that. But it turns out that in the Chern-Simons theory, with finite level, there's going to be a factor here. That I have to put a Q in front of this term and a Q inverse in front of that term. This is known as a Skene relation. And the reason for why this Q appears is because the gauge field basically is no longer going to commute with itself. There's going to be some delta function commutator between two gauge fields if I start quantizing this theory, because there's a time derivative here, so A doesn't commute with itself. If you boil it all down to a property of the Wilson line, it has this very simple rule. So this was really the hallmark, and maybe in some normalization this is actually a half. This might be a better formula, actually. So this Skene relation is really sort of the thing that drives the computation of Jones polynomials in Chern-Simons theory. Turns out that that relation is going to be sufficient for me to do the computation. So let me now sort of speed it up in the last 5 minutes. So what I need to do is I need to introduce a Wilson line that goes between the North and the South Pole. Now there's a slight subtlety which has to do precisely with the nature of the singularity at the North and the South Pole. But basically what happens is that because there's a singularity there, I basically have a little frame in the gauge group so that I can actually define a gauge invariant version of an open Wilson line between the North and the South Pole. So that's the nature of that particular singularity. Let me call this variable here Z. So what I'm going to do is I'm going to take the intersection between Z, and if this is the North Pole and this is the South Pole, then Z looks like that, and W looks like this. Right? W is the thing that goes around this, like this, and this is, I'm just drawing the same picture, but I'm drawing it here. If I now use that particular rule, then what's going to happen is that this thing is going to be Q to the half times this. This one. Am I doing that right? Yeah. Plus Q to the minus a half. Right. Locally, this what I'm doing with this intersection, I'm unpacking it in these two different ways. Okay. I'm going to call this Wilson line y, y plus 1. Let's say, let me call this thing y1, and this thing y minus 1. So here I have a relationship that quantity z, which is this quantity times that quantity, which is w, is q to the half times y plus q to the minus a half times 1 times y minus 1. It turns out that there's one more relation that I need because this already is very suggestive. Because what I can do is I can divide this relation by z. And then I can express w as a sum of two terms. Now, if you recall, previously when I wrote down the Hamiltonian of the SYK model, the Hamiltonian of the SYK model was an A plus an A dagger. This thing is essentially going to be my A. This thing is going to be my A dagger. It turns out that this thing is basically q to the power n. But anyway, I'm going to divide here. And there's going to be one more relation that sort of seals the deal. And again, that relation is sort of, again, the classical version of this relation. But to write it, let me, how am I doing with time? Probably I'm done with time. I have 2 more minutes, okay. There's a relation that's called the Ptolemy relation. Ptolemy lived in more than 2,000 years ago, and Ptolemy made a generalization of the Pythagoras theorem. So the way I'm going to unpack this equation is to think about this sphere literally as the Earth, where this is the North Pole and the South Pole. And I'm going to do the projection of a map. So if you look at the map of the world, typically it looks like a square. But this line here is the North Pole. This line there is the South Pole. Then this thing here is where W sits. And you know what? Let me put Z over here. So this line is W, this line is Z. This line is also Z because it's periodic, okay? But then Z times W is equal to Y1. So Y1 goes between the North and the South Pole and then traveling once towards west. And this one is Y2. Y minus 1. Okay, we're okay with that? So quantum mechanically, there's a q and a half here and a q to the minus a half here. If q is equal to 1, this is actually a classical relationship, which is true in geometry. And the classical, but there's another classical relationship which says the following, is that z squared, the square of z, is equal to the north and basically the square of, sorry, how am I doing this? Right, one more time. Y plus 1 times y minus 1. It's the product of the two diagonals. Is north times south plus z times z. So, so the product of the diagonals is the sum of the product of the north and the south times those two. So that's the Ptolemy relation. Turns out that I can normalize my path-ordered exponentials so that the north and the south holonomy is actually equal to 1. That's a definition of a normalization that I can choose. And then I get this particular relationship. And now comes the dictionary. I claim that Z is going to be Q to the power n. 1 minus Q times A, y plus 1 times Z to the power minus a half. 1 minus Q times A dagger. Y minus 1. Z, maybe the Z in front of it. I claim that this relation, in combination with this relation, in combination with those definitions, realize the Q-deformed harmonic oscillator in terms of the variables of the gravity theory. So basically, the phase space of the gravity theory, if you quantize it, reproduces the same algebra as that you're seeing in double-scaled SYK. And let me write down the last formula. It turns out that the Newton constant, which sits here, in the relationship with the Chern-Simons formulation, this turns out to be e to the 8 pi g Newton. So the dictionary between the SYK model is that it's written over here, and the gravity theory is that these line operators, and they represent these Q-deformed harmonic oscillators. The Q parameter, which was e to the minus lambda, which is e to the minus 2p squared over n, is going to be related to the Newton constant in this particular way. So that's the dictionary. Since I'm running sort of out of time, I'll stop here. And there's a question hour coming up, so we can take a 1-minute break or a 10-second break and then start the question hour.